Okay, again, good afternoon. Welcome to the robotics module. Today, we will have an introduction to robotic manipulator. Before that, regarding the drop period, I think for semester 7, you have time until 25th, if I'm correct, right? But the problem is we cannot wait until 25th to begin the practicals. So I'm thinking of finalizing the groups maybe by next week, so that at least we can start the practicals, because I don't think you need 1 month to decide whether you are taking the module or not, because we just can't wait that long. If we do that, you will have all the things at the end, which I don't think a good idea, right? So let's try to finalize by next week the groups for the practicals, as well as for that final group presentation. I will send you an announcement regarding that. So let's try to do that next week. Okay. So with that, so this is the outline for today's lecture. By the way, I hope you can see my screen as well as you can hear me. If someone can tell me yes, I can proceed.
Yes, sir.
Right. Okay. Thank you. So this is the outline for today's lecture. First, we will understand what a robotic manipulator is. And then we will have a look at the symbolic representation. And after that, we will define some terms such as configuration, degrees of freedom, workspace, and so on. After that, we will classify robot manipulators into different categories. Okay, and finally, we will go through the course outline, and the reason I kept it for the second lecture is actually, with the knowledge of robotic manipulators, it would be easier to understand these concepts, right? So we will look at forward kinematics. We'll try to understand what it means, at least. Later, we will have separate lectures on these concepts. Then we will understand what it means by inverse kinematics today itself, and then velocity kinematics. And next we will go through path planning and trajectory generation, and finally force control of manipulator. So what is a robotic manipulator? Now, if you can remember, in the last lecture, we mentioned that George Devil, he filed the first patent for a robot in 1954. So this robot called Unimate was a robotic manipulator, right? So he, together with Joseph Engelberger, who's known as the father of robotics, so they formed the first robot company called Unimation, and their first robotic manipulator was installed at General Motors. So here you can actually see that first Unimation robot at General Motors in 1961. So these robotic manipulators are typically arm-like robots, right? So there is a fixed base attached to the environment, and it will perform some repetitive task in a confined cell. So this is like a working cell, and it will do something that is programmed. And because of this fixed base, it won't be able to move beyond that designated area, right? And I also mentioned that these robotic manipulators or industrial robots those days were used in industries like metal, chemical, electronics, and food industry. Right. So a robotic manipulator is nothing but links connected by joints to form something called a kinematic chain. Okay. So we have a set of links. So it can be some metal or steel kind of rod kind of thing, right? So they are connected by joints, right? So if I draw a basic robotic manipulator, so we have a fixed base here, right? And then we have link, and let's say we have another link like this, and there can be a special joint so that some tool, or we call it as the end effector, attached to this final link, right? So again, let me name them. So this is a link, and this is also a link, and this is also a link. So we call this final one as the end effector, or let's say E, right? And these are the joints that connect these links, right? So we have one joint over here, and also there is another joint which is a little bit different from the previous joint. Here, actually, let's say the motion is lateral like this. So it's a change of maybe distance in that case, right? So here are some images for basic robotic manipulators, right? So they can come in different shapes, but the fundamental idea or the geometry is pretty much the same. And you can see in this third rightmost image, it's like an assembly line, and you can see this car moving in this assembly line. And what you see here in yellow color are also robotic manipulators, right? Okay. So when it comes to joints, I told you the joints is the mechanism to connect two links, right? And there are two main types of joints. So first we have the revolute joint. Let's call it as R for revolute. And then we have something called a prismatic joint that you actually saw in the previous slide also, right? So if I go back to this previous figure, so here what we have is revolute joint, and here it's a prismatic joint, okay? So what is a revolute joint and what is a prismatic joint? So revolute joint is basically a mechanism that allows the two links connected to have relative rotation, right? So you can see in this hinge, so this is a hinge, right? Here we have that particular revolute joint, and this is link 1 and this is link 2. And link 2 can have a relative rotation or orientation with respect to the previous link. So that is what is accomplished by a revolute joint. On the other hand, here, if I play this video, you can see we have a prismatic joint, and it allows relative translation between these two links, right? And another important thing to note is that the rotation or the orientation does not change even when it is in motion, right? So it maintains the same rotation, unlike the revolute joint. but it changes the relative distance. We call it as the translation, right? So here. So are those the only two joints we encounter? Do you recall any other joint types? Can somebody give an answer to that? Are these the only joint types that we know? Have you heard of something called a universal joint? Right? Actually, all these other types of, so let me mention that here, right? So we have other types of joints as well, but all these other types of joints can be created using this basic revolute and prismatic joint, okay? So if you take this universal joint where you can have rotation in any axis, right? So that is basically a combination of three revolute joints, one for each axis, let's say X, Y, and Z, right? So if we put three revolute joints at the same location, then we can actually have this orientation change in any direction, right? So we will only discuss about these two main types of joints, because any other joint, as I mentioned earlier, can be created using, right? Okay, so we'll move on. Now, when we draw robotic manipulators on paper, we should have some symbols to represent, particularly the joints. Okay, so in 2D, as you can see in this table also, we can use like this kind of a symbol here, right? To mention or to show a 2D revolute joint. And in 3D, so it is pretty understandable, right? So you can use this kind of a symbol to show a 2D revolute, 3D revolute joint. And here you can see a symbolic representation for a prismatic joint in 2D. So you can see what we are achieving is a motion, a linear motion between the two links, right? And again, in 3D, we can use something like this, right? Now, when we number the links and joints, we usually use some kind of a convention, right? So convention is nothing but one person who came up with the idea, numbered the links and joints like that, and the rest of the people agreed with that, right? So let's say I have a link, a joint, and another link like this, okay? And I'm going to call this as link I, right? And this is going to be link I plus 1. So this joint, and that number I'm going to give is I plus 1, right? And for each joint, I'm going to assign an axis, and we use usually Z in that convention. And that axis is, using that convention, this is going to be ZI. So you can see these two are connected, and these two are also connected, right? So you don't have to ask me why you are doing like this, because it's a convention, right? Somebody thought of doing it like that, and we are just following that convention. Right? Okay. Now, let's say we have a revolute joint, okay? So in a revolute joint, this ZI actually tells us the axis of rotation, okay? So this ZI over here, this one, tells us the axis of rotation. But if it is a prismatic joint, something like this, then it gives us the axis of translation, right? So if we have something like this, Now this is going to be our ZI, right? The direction where it translates. Okay. Now you know that we actually attach an actuator to the joint. So in this case, right, let's say we have a revolute joint, then we can attach, let's say, a motor, so that we can actuate this particular joint. And when we do that, link I+1 actually rotates with respect to link I, right? And also in the translational case, so the prismatic joint, we can use some mechanism to actually achieve this motion, right? Therefore, what we have here is a variable, right? So if it is a revolute joint, we are going to have a joint variable theta. So let me write it here, because we are talking about an angle of rotation, right? So we are measuring some angle theta. And when it is a prismatic joint, we have a distance, change of distance. So we will use d for distance, and that is basically some translational distance. I hope you understood that, right? So we'll move on to the next one. Now we know that a robotic manipulator has several joints, right? So it can be 3 joints or 4 joints usually, or it can have multiple joints go beyond 6 or 7 as well, right? Now I told you each joint is associated with a joint variable. So it can be either a theta or a distance, right? So the state of all joint variables, we call it as configuration, right? So let's say I will have some manipulator. I will use the same thing as before, right? So we have the end effector. So here we have our first joint. I will call it as Q1. Here we have Q2 and here Q3, right? So my configuration of this robot is Q is given by a vector Q1, Q2 that goes until Qn, where n is the number of joints, right? So these are my joint variables. Variables because those will change, right? So we will have some kind of actuating mechanism connected with the joint. So when we actuate either a motor or any other mechanism, so this Q1, Q2, and Qn, all these will change, right? And also remember, some Qs will be angles, so that is measured by, let's say, radians, and some Qs might be distances, not measured by meters, but something like centimeters. So because meters having that kind of a translation is going to be too big, right, for the manipulator, right? Now we make 2 assumptions during this course. That is, we assume that the manipulator is actually rigid, right? So these links are, let's say, made out of some steel or something, where they are not compressed or they can't bend or elongated, right? So that's actually a valid assumption, I suppose, right? So we assume the manipulator is rigid, right? So only using these joints, we can have different configurations, right? Other than that, the links we assume as rigid. And also the next assumption that I already told you is we assume that the base is fixed. Okay, so this guy over here is fixed, right? It's not moving. And when we make these 2 assumptions, actually, when we are given with the configuration, So configuration is this one, right? So when we are given with a configuration, can we draw the shape of the manipulator? Do we know the location of every point on the manipulator? Yes, right? Because we just need these few numbers. And if we know that, let's say we take the same manipulator, right? So I tell you that Q equals pi over 2, and the next one minus pi over 2, and let's say this next one is 1, whatever the unit, right? So when I give you the configuration, do you know how the manipulator looks like? You should be able to draw it, right? So here, this should be vertical because this angle is given as pi over 2. Let's say we are measuring angle like that, okay? So for the next joint, actually we measure with respect to this axis. These things you will learn later, okay? So it is minus pi over 2, this direction. So next link is going to be like that. And then we have maybe this is, let's say 1, shifted 1 to the right, okay? So now we know the location of every point of the manipulator because we assumed it to be rigid and the base is fixed. Understood? And finally, we have something called configuration space. So configuration space is the set of all possible configurations, right? So since we have several joint variables, the joint variables can take like many values, right? So it's like a continuous random variable, right? There can be many values here, and this can take many values, and this can take many values, but there can be some constraint. Let's say from 0 to 1. We don't have all the values here, and here maybe our joint can only operate from minus pi over 2 to plus pi over 2 because there are some joint constraints, right? Let me also show that. So if I start the video, I hope you can see. So if I take this elbow joint, right? So I think you can see, I can't like move it all the way. So there maybe it starts with, let's say 30 degrees and it can go up to pi, right? I don't want to move beyond that, right? So there is some constraint, right? So within that, you can have any angle between. So that's the joint constraint, right? So set of all these possible configurations, right? So there can be many, like a lot of combinations. Yeah, all these combinations of these, that is what we call as the configuration space, right? So for each configuration, the manipulator will end up in whatever shape, right? All right, we'll move on to understanding the next concept. So it is the degrees of freedom. Now in dynamics, that you might have covered in the first semester, and if you, let's say if you chose the mechanical engineering stream, these concepts are like discussed in a lot of detail, but we are not going to do that here, right? Okay. So we will only understand what we need for this robotics module. So, by the way, anyone knows what it means by the degrees of freedom? So the simplest way to tell it in our sense is, it is the dimension of the configuration, right? So if I have Q equals Q1 and Q2, so this is like a manipulator with two joints, right? So the degrees of freedoms are 2. So there is 2 degrees of freedom based on these two joints, right? And just I will give you another example. So what's the degrees of freedom here? It's 4, right? Because we have 4 joints and the dimension of the configuration space is 4, okay? But when it comes to learning dynamics, we have other ways to describe the configurations, sorry, the degrees of freedom, but we are not going to talk about it. Now, if you take a robot manipulator, so it's basically, as I told you earlier, degrees of freedom is the number of joints, okay, here. An important thing to note is we need at least 6 degrees of freedom to reach a given position. So let's say this is our target position, right? There is something there that we need to pick. Now, to reach a given position with given orientation, that is not just we go there, but we have to keep the end effector in a whatever orientation we would like, right? So again, if I start my video, let's say I'm going to approach a certain point, right? Here, approaching is one thing, but approaching with a given orientation like this is another thing. It's an additional thing, right? So approach, maybe we can actually do it with 3 joints because you know, for a 3D position, X, Y, Z is there. So if we can control that, then only 3 joints is needed to actually go to a certain point. But let's say we need to have whatever the orientation. So this is like a coordinate frame. Okay, I'm showing here. So to go, not only go there, but to have a different orientation. Now, why we need different orientation is, let's say we have a screwdriver that we need to rotate, right? So this is like a only one axis rotation, right? But if we need to achieve this rotation or else another rotation, so likewise, we need to keep the screwdriver in whatever orientation we would want. So in that case, we need 3 more degrees of freedom that we will learn later. So in orientation representations, something called the roll, pitch, yaw. Okay, don't worry about it right now because we have separate lectures for this orientation representation. Okay, so just remember for today that we need 6 degrees of freedom to reach a position with given orientation. Again, let me write it. So X, Y, Z, that is 3 for position. And let's say roll, pitch, and yaw, that is the 3 orientations, right? 3, 4 orientations. Right. So before we move on to the next one, we have something called a redundant manipulator, right? Now, I told you 6 degrees of freedoms is enough to approach some point with a given orientation. So why do we need redundant manipulators? So redundant manipulators is basically a manipulator with more than 6 joints. Okay. So we need these kind of manipulators, or what the so-called redundant manipulators. For example, in cases where we need to avoid an obstacle, right? So let's say I have a simple manipulator like this. So I can very nicely approach this one, okay? But if I take the same scenario where I have these obstacles in the environment, so can 2 joints accomplish this coming to this target position? Actually, you can't, right? So maybe, so I'm just maybe you make, but I'm just giving an example. Let's say if we have many joints like this, right? Then we can actually approach it, right? So this is like if you look at a snake, so it's like many number of joints connected together. So it can go through these kind of obstacles without hitting them, right? So that's some scenario where we need sometimes more than 6 degrees of freedom. Okay, let me ask you a question, right? So if we look at the human body, right, how many degrees of freedom do you think a human body has? So I need an answer from somebody. Can anybody think like based on these definitions that we just learned, how many degrees of freedom a human body has? Any guesses? If I help you a little bit, so I told you degrees of freedoms are like not like the number of joints, right? So how many joints do you think we have in the human body? Any answers? So if you take the, let's say we take the right hand, okay? So here we, I hope you can see. So here we have the shoulder joint, which looks like a universal joint, right? So when I say universal joint, that is like 3 revolute joints in the same place, right? So we have 3, and here maybe like let's say only 1. So 4, and how many here? So likewise, can you come up with a number? Any wild guess without the help of Google? Can somebody give? It's okay. I mean, okay, the exact count even I don't know, right? But I can give you a rough number. So let's ask Asita, Divisekara, what do you think?
As I think it's 10.
No, it's way more than 10. Human body has more than 10. Any other guesses? Himanta, Pyushan, do you have any number in your head?
40?
No, again, it's... So I'm just asking like how many joints are there in the body, right? If I give you another hint, just look at your palm and the fingers, how many joints? So for one finger, you have like 3 joints or 4, right? So that multiplied by 5 for the 5 fingers, right? So there you have 20. Any other guesses? What about Dilanka? Any guesses?
More than 300?
Now, now it's too big. So number is around 230, maybe 240 44 or something to be exact. But again, I also don't know the exact number. So that much of degrees of freedom you guys have. Okay. So please remember that. So it's just a matter of the number of joints. Okay. Right. We'll move on to the next one. Okay. So we have looked at the robot manipulator from the viewpoint of the joints, right? But now we will look at it from the position, let's say from the 3D viewpoint of the whole manipulator, right? So if you take the end effector for each configuration, let's say I have pi over 2, pi over 2, and 1. So then the end effector will end up somewhere, right? And for likewise, for all the configurations that we can think of, so in the joint space, we have in the Cartesian space where the end effector is going to end up. So if I show you this, right? So these are all the points where our end effector or the end tool will end up for different configurations, right? So for this particular robot, you can see the workspace is actually spherical, right? So you can actually go to all these positions using this particular manipulator. So that is my workspace, right? So if you use this manipulator for a certain application, the obvious first thing you need to do is whether whatever the thing you want to do is inside the workspace or not, right? Whether it is reachable or not, right? And it is constrained by the geometry of the manipulator, that is the shape of the manipulator, and the joint limits. Remember, I showed you for the elbow joint, it is maybe from 30 degrees to pi over 2. Right? So that is the joint limit. So every joint in the manipulator will have joint limits, and therefore the shape I'm going to create by sweeping the total volume will have a certain shape. Right? Okay. So let's say this is that workspace, right? So workspace, reachable points. And inside that, there is a subset called dexterous space. Dexterous. Okay, so that is also reachable points with arbitrary orientation, right? So for these points, I can approach with any orientation. So I can have the end effector tool in whatever the orientation I like. But these other, say this is the dexterous, these we can approach, but maybe when we approach it, the orientation will be fixed. We cannot change it. Okay. So remember these terms, right? It's just for your understanding. All right. Now we are going to classify manipulators into different categories. Okay. Now we can actually categorize these manipulators based on different things. So first, we can categorize based on its shape, or we call it the geometry or the kinematic structure. And next, we can also categorize based on the power source, right? So for these joints, when we are talking about the power source, we are mainly talking about how we are actuating the joints, right? So we can electrically actuate, that is basically we can have stepper motors or DC motors, right? At the joints, or else we can have pneumatic, or we can even have a hydraulics, right? So whatever the source, we can actually classify the manipulator based on this one. And finally, the relatively easier classification is the application area, right? Based on what application we are going to use the manipulator. So why do we need to classify, right? I mean, is like, are there many manipulators that we have to work with? So why do we need such a classification? Now, the reason we classify is that would actually help us determine which robot is best for a given task, right? Because from application point of view, let's say what we are looking at is to fulfill something using a robot, okay? So that is our the application. Let's say I have a factory where I need to automate the process of food production or something like that. So that is my application. Then I need to think what type of robot should I use. So then you actually know different types of robots based on its shape or the power source and application area, right? Uh, for example, let's say food handling. So I can't be using a hydraulic robot for that particular thing, because we know when you are using hydraulics, there's always leaking fluid. So that is not a good choice, right? And then let's say I have an assembly line where I need to do automobile spray painting, right? So in that case, if I tell you right now, a SCARA robot would not be suitable, you might not really understand it right now. But today, at the end of this lecture, you will agree with me, right, on this. So a SCARA robot is not the best choice for automobile spray paint. So once you finish this course, you should be able to quickly say, okay, maybe for this particular application, we should use this kind of a robot. Okay, so that knowledge is important, because we are always looking at the problems, and we will think like bottom, from that, we will go backwards to think what kind of a manipulator that we should choose, even let's say at the end in an examination question or something like that, I will give you the problem. Okay, you have this and that. So what type of manipulator are you going to choose? So that should be an engineering decision that you have to make as an engineer, right? So you, out of all these manipulators we will go through today, you will quickly say, okay, this is the best one for this particular application, right? So that knowledge is very important. So first, out of these three main categories, we will look at classification based on robot geometry, right? So when we say geometry, we are actually looking at the shape, but then again, as it is mentioned here, we are going to look at only the first three joints, right? First, because there can be 6 joints. If we need a dexterous robot that can go somewhere, that means that can approach somewhere with whatever the given orientation, right? So I told you for that we may need a robot with 6 degrees of freedom, right? But for this classification, we are only looking at the first 3 joints, okay? Because we are going to consider the remaining part, let's say the wrist part, separate. That is for later discussion. Right? Now let me again draw some kind of a manipulator. Let's say I have one joint, and here we have one link, and let's say another one, and here let's say we have a prismatic joint, so that goes up and down, and I'm just arbitrary drawing here. So another prismatic joint, and let's say we have a revolute joint that can rotate like this, okay, and we have the end effector, right? This is end effector. So for this particular classification, as I told you, we will only look at these first 3 joints, right? So there are 5 most commonly used types in this category, right? So first, we have something called articulated, revolute, or anthropomorphic manipulator. And RRR means, so here, this, wait, yeah, this one. So this means our first joint is revolute, second joint is revolute, and this is also revolute. Okay, and anthropomorphic actually means human-like. Okay, so when I say human-like, it would have like a shoulder and elbow and wrist. So that looks pretty similar to a human arm, right? So that's what it means by anthropomorphic. And then we have spherical manipulator, and here you can see it is RRP. So when I say RRP, now you understand that it is, first we have a revolute joint, and a prismatic joint. Then the third type is called Scara manipulator. So in the robotics community, this is a famous manipulator as well. And it also has RRP, but later you will understand the difference, right? So revolute, prismatic. Or maybe I can say the difference right here, because here we are only saying that the joint is revolute, right? We are not saying which axis, right? So here, maybe this is coming outside the paper in this manipulator. So this is our Z axis, right? So maybe another robot might have this kind of a joint. So there, the Z axis is different, right? So even though that is also R, this is also R, the axis is different. So that's why even the same RRP can have different shapes. That's pretty obvious, right? Based on this axis. Next, we have a cylindrical manipulator, and it is RPP, that is revolute, prismatic, and prismatic. And we have Cartesian, prismatic, and prismatic. So there are no revolute joints in the first three joints. Later, maybe we can have revolute joint, but for the first three, it's prismatic joints. Okay. Now we'll have a look at this one by one, right? So we'll start with the articulated or the revolute manipulator, RRR. So here you can see the symbolic representation, right? So this is our symbolic representation. So if you can remember the convention, maybe you might not at this very beginning. So here we will have a link, and we start numbering for links with 0, okay? And this is actually the joint as well, somewhere here. So we have a joint, and we start numbering with 1, okay? And then this guy is link 1, okay? And this one is joint 2. This is link 2, and this is like joint 3. Okay, so this is the shape of this articulated manipulator, and a very good example of this is the famous Puma robot. Okay, so let me show you. So you can see here there is rotation about this axis, right? That is 1R. Then there is rotation about this axis, another R, right? Revolute. And here this, so it changes. So another one, revolute. Okay, so this Puma robot is a common or a famous revolute manipulator, right? Yeah, so we'll, I think you understood about this first one. Next, we have something called a spherical manipulator, and carefully look at its shape. Okay, so Just like previous case, we have this the base joint in the same manner. So let's say link 0 and joint 1 here, and this is link 1. Now this one, if we look at the previous one, it is again same, right? It's the same thing. But the third joint is a prismatic joint in this case. Previously we had a revolute joint. Here we have a prismatic joint. So that's the difference in the spherical manipulator. Right? Let me show you this animation as well. So this is a spherical manipulator. So it is doing some task. It can be anything, right? So here it is, let's say, it's drawing a spring-like thing, or it may be soldering something or welding something that we don't care at the moment, but carefully look. So we have here. So this is the prismatic joint, right? And this here is a revolute, and also here we have the revolute joint. Okay. Right. Now my question is, why is it called spherical? Can somebody give an answer to that? Anybody? Any guesses? Let's see. Okay, so now the participants are decreasing. Can anybody give me an answer? Why is it spherical? So the reason is actually we can represent here this position of the end effector. Let me draw it. So this one. So that can be described using spherical coordinates from this point where these z axes all meet. So here we have z0, z1, and z2. So from that position, we can describe this guy using spherical coordinates. I hope you remember. So we have this particular angle theta, and then we have this angle, azimuth angle, you can have alpha or something. And then this is like the radius, right, of that particular sphere. Okay, so that's why we call it as a spherical manipulator, right? So basically, we will have a spherical workspace due to this reason, right? And again, a common example for a spherical manipulator is called the Stanford arm. Maybe you heard it in the previous lecture, right? So it is a common manipulator as well. So it is a spherical manipulator, but one difference is there. In the Stanford arm, these three Z axes does not actually intersect at a common point. Okay, and you will learn the reason later also when we discuss the Stanford arm, why it is not created like that. Okay, so this is something you better remember. Okay, the Stanford arm. Right, we'll move on to the next type. So this is called the SCARA manipulator, and SCARA stands for Selective Compliant Articulated Robot for Assembly. So that's what it means, right? So here you can see pretty much a kind of similar shape, but you can see the directions have changed, right? So here this joint is pretty much same in all the manipulators we saw. This one has changed, and here the prismatic joint direction has changed, right? Previously, you saw that it was this direction, right? Here we have a downward direction, right? And you can see all three axes are parallel in this case. And again, it's good to have a look at example, right? So this is a SCARA robot. And by looking at it, can you tell me for what kind of applications it is more suitable? Can somebody tell? Because it's boring when when I speak to the screen like this. So the application you can see.
Pick and place.
Sorry.
Pick and place.
Yeah, of course. So some kind of pick and place or tabletop application, right? So that this is a good option. So now you have to think from the other way around. Let's say you have to build something, let's say, I don't know, like a robot that can do soldering on, which is there on a tabletop, right? So you have to think whether this particular robot is suitable for that. So you have to think about it, right? Now you can see why this SCARA robot, the question I actually asked before, is not suitable for like a spray painting of a vehicle kind of thing. So this is like very good and suitable for tabletop kind of applications, right? All right. Another thing is, so this is also RRP and previous one is RRP, right? So two RRP robots can differ from each other. So now you know the reason, right? So previously we had Stanford arm, and this is not the same as the SCAR, even though both are RRP robots, right? That's pretty obvious. So moving on to the next one. So here we have a cylindrical manipulator, and I think now you can understand why it is called cylindrical, because just like the spherical manipulator, now we can actually represent or describe this location using cylindrical coordinates, right? So here we have a theta angle. This is like the height in cylindrical coordinate, and this is like the radius, right? So we have that cylindrical coordinate system, and here you can see how it actuates. Right, so we'll move on to the next one. So the final geometric shape we will discuss is the Cartesian manipulator, right? So it is a PPP, that is prismatic and prismatic manipulator. And I think now you can also understand why it is called Cartesian, right? So just like we have X, Y, Z, so Cartesian coordinates. So by actuating these joints, right? So this one, that one, and this one, you can have a description of this point using Cartesian coordinates with respect to whatever the, let's say, from here. Oh, sorry, maybe yeah, it should be from here. Yeah. So let me show this one as well. So again, you can see this is also a good option for tabletop applications. And in fact, we have used this concept in two of the final year projects we did at the department, right? So if you remember, there was one called a farm robot, right? So we use this structure for the farming robot. And there was another robot for carom playing, right? So it is also something a little bit similar to the Cartesian structure. Okay, so this is something you can make use of depending your application. If it is a tabletop application, so this is another good option, right? So that's why we should know what are these existing robot manipulators, right? Instead of thinking from the scratch, you can know these things that are already there, right? Okay, so that is about the robot geometry. And next is about classifying robot manipulators based on the power source, right? Yeah. So there are three main power sources that we commonly use: the hydraulic, electrical, as well as pneumatic. And this table actually gives you some advantages and disadvantages, right? So this hydraulic one is very good for high torque producing. If we are dealing with heavy loads, right? Maybe we have to load, unload, those kind of things, then this is the best option. And the disadvantages are, as I also mentioned before, there's a possibility of leaking the hydraulic fluid, and also, we need peripheral equipment like pumps and all to actually have these kind of actuators, right? So that means more maintenance, and these are too noisy as well, right? Now, the ones that we use for medium scale robots is mostly the electrical actuators, right? So the Scara robots and the Puma robots, as well as those uh, Cartesian manipulators that we saw, it's is under this category, right? So where we can have DC motors or stepper motors, right, to actuate these joints. So they are cheap, clean, high control accuracy, but the problem is the low torque. Next, we have the pneumatic ones as well, but again, we have some advantages: cheap, simple, and clean, but it has very limited applications because the controlling precision is not that high. Okay, so we don't get to see many robotic manipulators that uses these pneumatic actuators. And I think this is something better to know, something called power weight ratio. So this is mostly found in vehicles. When we talk about vehicles, there we talk about the power weight ratio. So if you see this graph, you can see the DC motors in this particular area, where the hydraulic actuators, the power output is also high, and the weight is also high. So just for your knowledge, I have included this. All right. And the third classification I'm going to make is based on the application area, right? By now, I think, I hope you can like recognize this type of robots, right? So we have two main categories: the assembly and non-assembly robots, right? So these assembly robots are tend to be small and electrically driven. So here you can see again some pick and place or something similar using SCAR assembly robots. Okay, and when it comes to non-assembly, we have this heavy load, that kind of manipulators which can do welding, spray painting. So in mostly in let's say car assembly lines, what we see is these kind of larger robots, right? So here what you see in this picture is a welding robot. And the primary difference between these assembly robots and non-assembly robots is the level of precision. Okay, so for assembly tasks like peg in hole assemblies or gear meshing, we need increased precision. So for that we use assembly robots. So even the slightest mismatch between the parts can actually lead to jamming. right? So when that happens, there will be a large interaction force and failure can occur. Okay, right. So that's actually about the classification of robots, right? So when you see a robot the next time, I think now you should be able to classify robots into different categories. So mainly we looked at this geometry and also power source and the application area. Now let me give you a brief outline to what you would expect during this course. Right? Again, I'm telling you why I delayed it until the second lecture is because the knowledge of the manipulator would help you understand what each of these terms mean, right? So let me give you an example. Let's say we have a two-link planar robot manipulator. Now this two-link is actually a kind of a common mistake that we use, but we keep on using it. Here it actually has three links, right? This and this, because we normally forget about this fixed base, right? And the planar means so this actually moves in this particular plane, right? So this is just an example. So let's say we have a grinding tool. So here we have some grinding tool and we want to remove certain amount of metal from this surface. It can be anything else as well, right? So in order to do this, our first step is to move this end effector from the home position to, let's say, A position. Because when we start the manipulator, there would be a home position. I think you have worked with servo motors, right? So when you plugged in, there is some initial position like that, right? So let's say this is our initial position, right? So our first step is to move this grinding tool from here to there. And for that, actually, the trajectory we make is not that important, right? As long as it does not hit this camera, right? The way it goes from home to A is whatever is okay. But next step is to move from A to B, right? Let's say we are given with a certain contour, or let's say it can be some polynomial function or whatever it is, right? So there is some equation or something that we have been given to move the grinding tool from A to B. And while we are doing that, we need to maintain some velocity. And also it should apply certain force, because otherwise it will not grind this surface, right? So these are the requirements. So we need to move at a certain velocity and there is certain force. But what is the input of this manipulator? The input is only like this motor here, this revolute joint and this revolute joint. So we have to control this in the required manner by controlling these two motors, right? So there should be some mapping that we need to understand. So when this motor rotates at some RPM and when this guy rotates at some RPM, there will be a Cartesian or in 3 dimensions, there is some velocity for this guy, right? And here you have a torque, right? So the motor, in the motor, you have certain torque. In this motor, you have some torque. And that, so altogether, that should give this required force here. So this is the full course outline that we want to, that we will actually study in this course, how we map these things from here to there. Okay. So these are the things that we will actually look at. So we'll start with something called forward kinematics, right? So in forward kinematics, what it means is, So let me go through this sentence first. Representing the end effector pose. So remember, when I say pose, pose means position and orientation, right? Not only I want to go to some target location, but I need to have a certain orientation as well. Okay, so that is my pose. So I want to represent that using the joint variable. That is, let's say motor 1 or the joint 1 should have angle theta 1, and motor 2 or the joint 2 should have some angle theta 2, right? So let me draw it here. So let's say I have this some black box or something, right? So my input is these angles to the joints, right? So this is my input. My output is X, Y, and theta, right? So if I show you this one, so XY is this. This is X and this is Y. And theta, maybe let's say this is that angle theta, right? So forward kinematics is nothing but finding X, Y, theta based using theta 1 and theta 2. So that's all what it means by forward kinematics, right? In the forward direction. Now, if I draw that same manipulator in a simple manner, let me call this not just X, but X naught, okay? In robotics, we will be dealing with many coordinate frames that you will understand later. So that's why I'm calling this not just XY, but X naught and Y naught, right? And let's say we have our first link like this, and the joint is actually here, right? So in our discussion, this guy does not come into play. That's why this is mentioned as two link. Okay. So here we have a joint, and here we have another link. Okay. And let me call this as theta 1. This is actually the joint angle of the first joint. And here, let me call this as theta 2, right? So that is with respect to the previous link. That's why I drew this dashed line like this. So that's the angle of my motor or the servo or whatever that is actually fixed in this particular link, right? So this is where I'm interested. So let's call this X and Y, okay? And I will give this direction as theta. I will actually attach some more coordinate frames. Okay, so this is X1, Y1, and this is X2, Y2. Okay, so in forward kinematics, I want to find X, Y, and theta with respect to theta 1 and theta 2. Okay? That's all what we are doing in forward kinematics, right? Now, if I give you a simple question, right? Let's say I ask you, when theta 1 equals theta 2 equals 0, what is Y? And can somebody quickly tell me? Yeah. And theta 1 and theta 2 equals 0, what is Y? Quick, can somebody
Yes.
tell me? Sorry?
0.
I can't hear, sorry.
0.
Right, yeah, correct. So Y is equal to 0, right? And if I ask you what is X, you will say X would be equal to L1 plus L2, right? So this is actually, we are doing forward kinematics. So the input is theta1 and theta2, the joint angles I give to the joints, and I am figuring out where my end effector, or let's say it's a screwdriver or a paintbrush or a drill or whatever I have at that end effector, what's the position of that, right? X, Y, and also theta will tell you what's the orientation, because orientation is also important, right? And one more thing, so we normally establish a fixed reference frame. So this is my fixed frame, right? We call it as the base frame or the world frame, okay? And all objects are referred with respect to this fixed frame in this case, right? So we'll move on to some more development from this. Okay, now I'm asking you to find x, y, and theta based on these given information. So there are some constants that you can use, or as well as some variables, theta1 and theta2. So I'm basically asking you to find x, y, and theta with using theta1 and theta2, right? So I don't think you need paper and pen to even write it. So if you have it right now, please write it. And can somebody tell me what the answer is? And by the way, it's better to be ready with some paper and not just listening, because in the coming slides, we have some more things like this, right? So can somebody tell me the answer? It's better maybe if I ask. Let's ask Shaluta, are you there? So what's the answer? What is x?
Yes, x is L1 cos theta 1 plus L2 cos theta 1 plus theta 2.
Right. And y, what? Yeah, y.
Y is L1 sin theta 1.
So the participants are dropping. So don't worry. Actually, if you give a wrong answer, it's totally okay. I just want. I don't like to be the only person talking. That's why I'm asking questions, right? So, yeah, let me write it here. Or else I can just, keep writing and not ask questions. So this is simple as that, right? So this should be L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, so I hope you understood how theta 1 plus theta 2 came, because here this is only this particular angle, right? So we need to add this guy. And what is theta? So it should be theta 1 plus theta 2, right? So this is basically the forward kinematics, right? You find out x, y, theta, or the end effector pose. Pose means position and orientation with respect to theta 1 and theta 2. So if you build a small manipulator like this, right, now you know how to map it, right? So based on the angles, you know where your end effector is going to end, right? So these are called forward kinematics, but this is for planar or 2D case, right? So I think you can understand when we are dealing in 3D, these equations can get very complex, right? So later we will deal with those. Right, so that's all about forward kinematics. By the way, yeah, one more question, right? Now, if I ask you to write these equations, let's say vector form, like this. Can you fill the empty matrix? Yeah, so I'm not going to point at anyone. So if you are willing to answer, you can give me an answer. Right. Can you fill the empty matrix? Yes, anybody?
I think no, sir.
No, right? Yeah, if we can, then there's a problem with what you learned so far. So yeah, we cannot fill this empty matrix, right? But if for some reason, if we could, right? Let's say we fill this matrix like K1, K2, and K3, then this system we call as a linear system, right? For this whatever x and theta between these two. So let's say these are like vectors, right? If we could, for some reason, this is going to be a linear system. But unfortunately, as you correctly said, we can't do that, right? So let me write it again. Theta 1 and theta 2. So we can't do that. So forward kinematics, right? So this is not actually a generalization, but it actually is the case, right? So it's usually not linear. And when things are not linear, it's not very good, right? Because we have like 100 years of knowledge in linear algebra, all these things to solve these, right? But unfortunately, forward kinematics is not linear, right? So that's something you should know, right? Now, I think you know what forward kinematics is. So whatever the manipulator, let's say it's a scalar manipulator or cylindrical, if somebody asks what does it mean by forward kinematics of a scalar manipulator, is basically it's about the mapping of this theta angles or the distances that you give to the joints and where the end effector is going to end up, right? But the most interesting and the important is the opposite actually, right? That is called the inverse kinematics. So when we say inverse kinematics, right, we want to represent the joint variables based on the end effector coordinates. So if I draw again a black box right like this, okay, so my input is actually x, y, and theta, and my output should be theta 1 and theta 2. So if you look at it carefully, this is what we really want, right? Because let's say I want to drill a hole at a particular location of the wall, right? So that is like x, y, and theta. Theta can be, let's say, some angle. So in order to do that, we should know what are the joint angles that we should give to the robot joints. So that is the more valid questions when it comes to robot manipulators, right? So inverse kinematics is the actually the real problem we need to solve, not the forward kinematics, right? So if I again show you this same figure, I told you we need to send the end effector from home to A. So for A in the physical like dimension, we know where A is. It can be 10 meters from here, X direction, and 10 meters from Y direction. And I'm assuming, let's say, this is my final direction theta, right? So I know X, Y, and theta, right? So I need to find this theta 1 and theta 2 to actually send that guy to there. So that's the real question we need to solve, and that question is called the inverse kinematics problem, right? Now, as you can understand, inverse kinematics problem is harder than the forward kinematics problem. And maybe the solution you can't find. So it is, let's say, not easy to find, right? And there may be situations where we don't have a unique solution, right? So when I say unique solution, let's say I have the manipulator like this, and this is my target location. So this is one solution, right? And this can be another solution. So this we call as elbow up solution, and this is elbow down solution. Okay, so these are, there can be many solutions as well. So that is what it means by no unique solution, right? And sometimes there might be no solution at all. So just imagine this is my target point where I want to make a hole, right? Now, if we even have our manipulator like this, maybe it cannot reach it, right? So if I give this x, y, and theta, my answers for theta 1 and theta 2, we can't find, right? So there's no solution. So there are many such problems regarding inverse kinematics. The obvious problem is the first one. It is not really easy to find. And let's go back to this previous one. Then you can also understand it, right? Now I'm asking the question, given x, y, and theta, I want you to find theta 1 and theta 2. Can you take like 5 minutes to actually do this? Can you try to find theta 1 and theta 2? Okay, I will give these values, right? So this is L1, because these are measurable and we know beforehand, right? Can you give some effort to find theta 1 and theta 2? At least to understand that it is difficult. So I'm hoping that you are trying. So I will give you a hint, right? So if you take this OAB triangle, right? So that means complete this triangle OAB, right? And if I apply law of cosines OAB to this OAB triangle, let's say this is L, right? So I can write L squared is equal to L1 squared plus L2 squared minus 2 L1 L2 cos, what's the angle? Phi minus theta 2, right? This angle we are talking about, right? So this is cos minus, right? Cos theta 2. Therefore, cos theta 2 is equal to L squared minus L1 squared minus L2 squared, whole thing divided by 2L1 and L2. Now we have an unknown called L, right? So what is L? L is actually, you can see L squared is equal to actually x squared plus y squared, right? That is from this big triangle, this one. right? L squared equals x squared plus y squared. So we can maybe put that here. Now I did this quickly because I already knew it, how to do it, but otherwise it would have taken you some more time. Not like the forward kinematics where you just wrote x equals L1 cos theta 1 plus L2 cos theta 1 plus theta 2, right? So the inverse problem is not straightforward most of the time, and it actually depends on the manipulator, right? So there is no like a general way of doing it. So for the manipulator, you have to think of all the geometrical relationships and come up with the answer, right? Therefore, theta 2, now we found theta 2, that is cos inverse. Let me call this whole thing as Q. Okay, cos inverse Q, right? Now, can you find the theta 1? Again, it is not straightforward, right? So let me call this, maybe, of course, there should be other ways that you might have done, but since in the online mode, I can't check those, right? So if we take this as beta, right? So I can write tan beta, where I will draw this triangle, okay? So I'm talking about now this triangle. So tan beta is actually L2 sine theta 2 over L1 plus L2 cos theta 2, right? So I'm talking about this distance and this one, right? So from this, we get theta 1 equals, okay, this is only beta, right? Now, we are looking at this guy, theta 1, right? For theta 1, we know that tan beta plus theta 1, that whole thing is y over x, right? This beta and theta 1 thing, right? So from that, I may write this as an inverse y over x, that whole angle minus tan inverse L2 sine theta 2 L1 plus L2 cos theta. So this is actually this guy, right? I hope somehow you understood what I was saying, right? So this theta is this whole angle minus beta, right? Okay, now we have two answers, right? For theta 2 and theta 1, right? So if you didn't understand it, maybe slowly later you can have a look at it, right? So these were the two answers for theta 2 and theta 1. And if I again ask you the same question, now I want to find theta 1 and theta 2, right? With some matrix times xy. Can we do that? I don't think so, right? So this is also not possible. So unfortunately, inverse, oh, sorry. So inverse kinematics is also not linear, right? So these are all non-linear problems that we are dealing with, right? Okay, so that is about the inverse kinematics. So let me quickly go to the next one, which is velocity kinematics. Now things get a little bit interesting than the previous two cases, right? So when we say velocity kinematics, it is about establishing relationship between the velocities. So previously we talked about positions, right? But now we are talking about velocities. So can we have a mapping between the tool velocity and the motor velocities? So that is also important, right? So these are the forward kinematic equations that you learned before, right? I mean, just we derive x equals L1 cos theta, this and this, right? Now, shall we differentiate this with respect to time? Again, so can you give it a try? It's very I mean, for a fourth year student, I don't think that this is a very hard problem, right? So can you try to differentiate this? So the only thing to note is we are not differentiating with respect to theta 1 or theta 2, but with respect to time, okay? D by dt. So there's one thing to note. So can you take like 1 or 2 minutes and write? So I want you to write what is x dot and what is y dot. So if I start writing the first one, so we have L1, now cos theta 1. So if we differentiate it with respect to theta 1, we get minus sine theta 1. But what we actually need is with respect to time, right? Therefore, this should be theta multiplied by theta 1 dot. Very easy mistake to make, right? That is our first term, and then next term again L2. So cos, again we get minus sine theta 1 plus theta 2. Then again we have to do it with respect to time. So we will have this as multiplied by theta 1 dot and theta 2 dot. Right? Again, if you have any questions, please let me know. This is very much one-way teaching, but unfortunately, I don't know any other way to interact you. So next line, L1 sine theta becomes cos theta 1 times theta 1 dot, right? L2 sine becomes cos, this term multiplied by, now with respect to time, right? Right. I hope at least few of you got this answer right now. And if you didn't, don't worry, you can slowly have a look at it. Now, again, I'm asking the same question. So I have x dot, y dot equals something, theta 1 dot, theta 2 dot. At least can somebody tell me whether this can be done or not? Yes?
Yes.
Right. So now we have an interesting situation, right? So I want you to write these matrix elements. So first we will have L1 sine theta 1 minus L2 sine theta 1 plus theta 2, L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Here we have L2 sine theta 1 plus theta 2, L2 cos theta 1 plus theta 2, right? So this we can write as, so this is like a, let's say, taken as a vector, okay, x vector, and this I call as the Jacobian J, right, and theta dot, right? So J is the Jacobian. I hope you understood, right? So that's actually good news, right? So when it comes to velocities, so we have the possibility to write it in this fashion. So this means velocity kinematics is linear, right? And that gives us more options or more advantages. So if I go to the next page, right? So this equation is linear, and most importantly, we can find the inverse, right? So that's actually what we need. It's not about finding what is going to happen to the tool if I give some motor velocity, sorry, but the opposite, right? I want to find the motor velocities if I know the final velocity of the tool, right? So theta dot, so that this vector is going to be J inverse, the Jacobian inverse times this one. So this is the very important relationship we can actually find. From whatever linear algebra knowledge we have, we can find what are the motor velocities that we should give to the actuator so that we will achieve, let's say we want to paint, and it should go up and down at, I don't know, like 5 centimeters per second. So we know that 5 centimeters per second beforehand, because that is how we say paint or whatever, clean or whatever, right? Now we know from this what are the motor velocities that we should give to achieve that particular velocity. So that's the understanding I want you to have. Right? And okay, can you try to find J inverse? I hope you remember a 2 by 2 matrix, right? A, B, C, D inverse. Do you remember the inverse of a 2 by 2 matrix? This should have been very interesting if we had these physical lectures, but can somebody tell me what's the inverse of this quickly, if you can remember?
A joint over determinant.
Yeah, that is for any matrix, right? Inverse
AD
is for 3 by 3, 6 by 6, whatever. But I'm just asking for a 2 by 2. Do you remember like a shortcut? If we have A, B, C, D, so do you at least remember changing this D and A and making this minus C and minus B? And here we have, of course, the determinant AD minus BC. Maybe you have somewhere came across this one, right? For a 2 by 2, this is the equation. So if you apply that to this particular Jacobian matrix, right? So I will interchange the diagonal elements. So L2 cos theta 1 plus theta 2 comes here, and this guy comes here, L1 sine theta. So all what you learned so far becomes useful little by little. Okay, so here we get the minus of that. And here also we get the minus of that particular element. And we have to divide this by the determinant. So I will maybe write it here. So if you find the determinant, you will find that is equal to L1 plus L2 sine theta 2. Okay, so that is our Jacobian inverse. And also remember, Jacobian is not a constant, right? So depending on the shape, the configuration. So at one instance, the Jacobian is something. Another instance, the Jacobian is something else. So you can see theta 1 and theta 2 are involved in this matrix, right? So the Jacobian changes. So if I ask you, what happens when theta 2 equals 0? So here you can see in the determinant, we have sine, here, sine theta 2 part, right? If theta 2 equals 0, we have 1 over 0 term where the Jacobian goes to infinity. So that means, right, the Jacobian does not exist for certain configurations. And that is something we call as a singular configuration. Okay, so for the manipulators, we have these singular configurations and we need to actually avoid that. Otherwise, our manipulator can get stuck. Let's say we are calculating joint velocities and it comes to some kind of a singularity. So we call this as a singularity. So at that position, we don't have the Jacobian and we are unable to find what are the motor velocities that we should give, right? So let me give you this example. So this is that case where theta 2 equals 0, right? So it's a pretty simple scenario, right? The second link is in parallel with the first link, right? Here. So this is our angle theta 2. Now let's say I want to give some velocity in this direction, right? I want to have some x2 dot, right? Now, since this is a singularity, you can really understand because this is like the maximum point. So we are unable to move further, right? So that means we are unable to calculate the motor velocities. Or it is like infinite, right? To achieve a motion in this direction. Right? So certain motions are unachievable at these kind of singular configurations, right? So this we will talk about these later with greater detail because these are very important. Let's say we built a manipulator and sometimes if we pass through a singular point, then everything goes like chaos, right? It can get stuck and we don't know what to do after that. At that singularity, it will get stuck or because we are calculating motor velocities that we should give and that particular calculator for motor that gives you very undesirable infinite answer. So things like that can happen, right? So we will talk about these singularities later, but here I'm just giving you the outline what to expect in the future, right? So all these are very important. Next, we have path planning and trajectory generation, and this won't take long, the two topics. So I will quickly go through it. No mathematics again, right, for today. So when we say path planning, we want to find a path to go from A to B, right? If I show you the previous this example. So here we have certain path, right, from A to B in this. So we need to plan how we are going to go from A to B, right? So it can be some equation, it can be a polynomial equation, or there are various ways we can actually approach it, right? So that is the topic for path planning and trajectory generation. one thing you should remember is like when we say path, it is like some spatial construct, right? But when we say trajectory, between the same point, we have the same path like this, but we are giving timing information, t equals 0, t equals 1. So by t equals 10, this guy should be here. And here when t equals 20, this should be here, right? So that is how we actually achieve efficiency in this, whatever the application we are using. Let's say we want to solder 5 PCBs in, I don't know, 10 seconds. So we have that kind of requirement, right, when it comes to a factory. So all this timing information comes into the trajectory diagrams, and we will study how we can actually come up with, let's say, a polynomial function and things like that. So we need to think about acceleration limits, because let's say we want to do it as much as possible. We want to solder many PCBs, but we know that there are certain limits for the motor. So there is a maximum velocity, there's a maximum acceleration that we cannot actually surpass, right? So that we will actually discuss under this. Let me show you this quick video, what it means by trajectory planning. So from some point to another point, how we are going to achieve that trajectory. Okay. So when you learn mobile robotics, all these fundamental knowledge will be useful. It's again a trajectory planning problem for the motion, okay? Something like this. So we want to go through this particular hole and go to the other side. So how are we going to plan it? Right. And finally, we have force control of manipulators. Now, again, we will not go into deep, because as electronics and telecom students, we haven't really covered much of the dynamic aspects, right? I think you might have learned some dynamics in the semester 1, but I'm sure you might have forgotten it most of the time. I don't know even whether you have heard the terms like Euler acceleration, Coriolis acceleration. And don't worry, we are not really going to deal with that, because it's a topic on its own, right? Which can be taught over a semester, but we'll try to somehow learn some simple things associated with this one, right? So basically, we are looking at what you need to actually understand is, if I show you this once more, we need, let's say, some force here, right? To crush or drill or whatever, or grind. So what we have is torque, right? Torque 1. So how can we achieve that particular force in terms of these motor torques? So that's basically the idea in this, right? And interestingly, the same Jacobian matrix that we learn in velocity kinematics can be used to establish this relationship, forces and torques, right? Okay, so that is the final topic in the course outline. So let me summarize what we studied today, right? So we started with how we can draw a manipulator on a paper, like using some symbolic representations, and we got to know what is the configuration, that is the state of all the joints, then the degrees of freedom, which is equal to number of joints, and the workspace, that is like the 3D volume it will actually sweep, right? Then we know some classifications of robots based on mainly the geometry. So there are RRP. So you saw what is a Stanford arm, SCARA robot. Now at least I hope you can identify certain robot manipulators, right? And then about power source and application. And finally, I went through what we will encounter in the coming lectures, right? So we'll talk about forward kinematics. So we give some theta 1 and theta 2 and find out where our end effector is going to end up, right? But the most important question is the inverse kinematics. We want to send the end effector to some position and an angle, and what are the inputs that we should give to the joints or the motors, right? What is the theta 1 and theta 2? And then the same concept but in velocities, right? If you want to achieve certain velocity, what is the motor velocity, the motor speeds that we should give, right? So that's about velocity and path planning and trajectories, like from A to B, how we can actually have a smooth trajectory, how we can create it, right? And finally, about the force control. So in order to get some force at the tool, what is the torque that we give to the motors, right? So most of in the previous like years, this force aspect could not be covered because of the limited number of weeks, but let's see if time is there, at least some knowledge I can give regarding the force, because this mostly in the mechanical engineering aspects, right? So that's why there are many things to cover if we are to cover this particular part, right? So let's see how we go. That is the end of today's lecture. Do you have any questions? Again, I will let you know about these groupings and all, because as I told you at the very beginning, we can't wait until 25th drop period to start practicals, right? Then you will, all the this will pile up. So that is again not good. Do you have any general questions regarding the module?